Hi, my name is Andrea Grumier, and this is my fourth lab for Physics 2. To introduce the purpose of this lab is to understand the effects of resistors in series and in parallel, and to model this behavior. So the results were that the capacitor in a circuit made up of a light bulb with smaller resistance took less time to charge and discharge, alongside other things following like circuits in parallel and in series, and then the calculated RC value was approximately 6.5 seconds. The fundamental physics principles explored during this lab are the following, which is Ohm's law, capacitance, energy and charge conservation laws, as well as, again, rules based on circuits in parallel and series. Other relevant formulas are the loop rule, the node rule, and the formula to calculate RC. So part one includes open and closed circuits, and I followed the following steps. So the assumptions for the model is that the circuit is a system and the surroundings are everything else. The resistance of wires and the resistance of the ammeter is negligible. And then following the loop rule, the sum of potential differences are the EMF plus delta V capacitor plus delta V resistor, which is equal to 0. For the closed circuit readings, I predicted that the current would be 0.0204 amps based on the values I had, but the actual current lacked the last two significant figures. In the case that we reverse the connections to one of the ammeters, it would still be the same magnitude, but opposite sign. For the open circuit readings, there was obviously no current flowing. And then the only potential difference would be the EMF, which is 3 volts. If we close the circuit again and note the delta V across different segments, we get the following values. And then if we sum the potential differences for the round trip, we actually get that it's 0 volts following the loop rule. The current does not change. It's still 0.02 amps because the voltmeter has a high resistance and therefore current doesn't flow through it. So it remains unchanged. The approximate potential versus position graph I sketched was following. We can see that there's a greater potential difference change from E to F than from C to D. The closed circuit ammeter reading in parallel to 100 ohm resistor increases to 0.06 amps because less current is going through the 100 ohm resistor since it splits up at the node, and ammeter has 0 resistance. And current increases because it is inversely proportional to V, so V must decrease. Since current is equal to delta V over R, we can calculate R for the following parts. And we actually get that the new values for resistance for the 47 ohm resistor and for the 100 ohm resistor are higher than the actual values due to the inaccuracy of the ammeter mentioned in the beginning for the lacking significant figures. Part 2, we studied RC circuits. For the charging capacitor, we observed that the current decreases from its maximum indicated by the bulb's radiance to 0, and the capacitor is uncharged when current is at its maximum, but fully charged when current is 0. And the charging times are substantially smaller for the 10 ohm light bulb. For the capacitor discharging, the following observations were made. The maximum current is T equals 0, indicated by the bright light bulb. When capacitor is fully discharged, there is no current flowing, and throughout the whole time, the current is actually flowing in the opposite direction to when the capacitor is charging. And then again, the discharging time for the 10 ohm light bulb was substantially less than for the 20 ohm light bulb. To determine the RC value, I made the following table. And these are the values for L and V at the present time divided by the initial voltage. And then it gave me the following graph, which has a slope of negative 0.154, which is a downward sloping graph. And this is equal to negative 1 over RC. Therefore, RC is approximately 6.5 seconds. Sources of error and discrepancy. There probably was no discrepancy in the linearization because it was a computational model. In actual data recording, the error might lie in like timing issues because I might have stopped the watch either too early or too late. To reflect, what if we had been doing this in a lab in real life and used an actual ammeter instead of an ideal simulated ammeter? Real life ammeters have resistance, therefore current would be expected to decrease. And if we use a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? If there is no resistor in the circuit, in the model, capacitor would ideally be fully charged immediately since current wouldn't slow down. But in real life, the capacitor would charge faster because although there is no resistor, the wires do apply a little bit of resistance, so it wouldn't be an immediate charge. Thank you.